In this unit, we're going to look at how we use an equation to represent functions. Remember, equations is just different rules that describes the relations between the input x and the output y. The equation will also generate ordered pairs. Pay attention to ordered pairs by taking an input that result in a certain output. And the graph of the equation is the set of all the ordered pairs, all its ordered pairs. You put it all together, which often forms a line or a curve, right? And so the graphical representation of a function very often is like a meat grinder that it's as illustrated here. It's actually kind of fun. So the input is x and you get to pick. So you pick whatever it is. That's why it's called the independent variable. And the output, it really depends on whether my inside is a linear equation, or it could be x squared, a parabola, exponential equation, or some other things. It could, maybe it's not mathematical, right? It's some other kind of logic. And whatever the output is, this output depends on the equations inside. So if it's a meat grinder, how fine do I set it? Or maybe a pasta maker, whatever comes out, whatever shape, depends on the setting. And the setting inside the machine is the function that we describe here. Okay, so So let's look at some of these slightly harder ones. You should go back and finish the easier ones once you see how I complete the harder ones, right? So here, x values are given, domains are given. I'm asked to find out the range, y. So I plug in each. Negative x becomes -3 plus 1. So double negative makes a positive. 4 plus 1 gives me 5. I'm sorry, 3 plus 1, 3 plus 1 gives me 4. So that's 4 there, my apologies. Now, same thing, let's do -1. So negative x, what is my x? It's -1. Plug it in, I should have 2. 0, -0, plug it in, I should have 1. So if I plug in 4, it becomes -4 plus 1 is -3. So if I were to graph this, I have -3, 1, 2, 3, +4, 1, 2, 3, 4, right here. And I have -1 here and +2 here. I have 0 and +1. You see the relations, how they're connected with each other. I have +1, 2, 3, 4 here, and then 1, 2, 3 right here. So now you see how they are forming a straight line. Okay? That's how you do it. Some of them, the curvy ones, may be a little bit harder to graph, but the concept is there. Oops, if I shrink this, it gets my graph all messed up. Sorry about that. So that should do. All right, let's look at some of the ones at the bottom. These, the domains are given, but I'm asking to find the range. So I will do number 9. Domain is all the x values. So you have to create a table and put your x values in here. Then you calculate it. It's 4 minus x. And if this, in the first case, x is -2, double negative makes a positive. So you have -2, 6 as an ordered pair. Now, same thing with 3. 4 minus x equals what? 1, right? Same thing with 5. Now you have -1. So now your range is this set. All the y values, 6, 1. I'm sorry, it should be in orders from the smallest to the biggest. So it should be -1, +1, and 6. So for all the remainder practices, get a table, throw the domains in there, calculate the value for each range, then put them together in the in this format, in the set format. It's a set of numbers that represent the range. Okay, so finish these 2 pages and pause the video before that. I'm going to move on to the next page. So this page is a summary of different ways to represent relations. We started out by ordered pairs, and if you look to the left, I have domains, and I can put that in a set of -1, 0, and 2. Is that right? -1, 0, and 2. That's right. And range, I can put that together. It's all the y values. And now, is this a function? Is it a one-on-one relations? Absolutely. Now, the second method, we did tables. So the domain is simply all the x values, but put it in from the smallest to the largest. And notice that I've got 2 3s here. So it's a repeat. In my set expression, it's just 3 is enough. And then for y, I have smallest is -4, 1, 2, and 6. Is this a function? Because there are 2 same inputs of 3s with two different y input. So I'm going to say that this is not a function. Next, we will do mapping, and domain here on the left, this is x, the input, right? Because the arrow points to the y. The domain is simply -7, 0, and 3. 3 different x values. And the range is 1 and 2. And this is a function. Remember, this whole thing is x-driven, is input-driven, independent value-driven, input-driven. So, excuse me. As long as each x value has one value, matching value on the y, you're good. It is a function. Equation is easy. For this equation, the domain is all real numbers. You can just write it like that. And the easiest thing is to plug this thing into a graphing calculator called Desmos. I did not spell that right. Desmos. And you will see, I've used it in class. You will see what it is like if you plug it in. And this should look something like this, with this point being -1. So, of course, all the possible y's on this, all the possible y value, all the possible y on this function has to be above -1. So y is greater or equal to -1. And is this a function? If I use a horizontal line test, absolutely this is a function. It only touches my pencil, or my saber only touches the function once in life at each point. Okay, so finally the graph. Let's try the domain. We use the vertical saber or pencil, and nothing, and x only touches the function between this value here on the x-axis and this value here on the x-axis. So that's -4 and +1. And so x is greater or equal to -4, less or equal than +1. For y, it's the same thing. Notice that. So y has to be less or equal to +3, greater or equal to -1. Is this a function? Another way to ask the same question, Does this pass the horizontal line test? Let's see, does it? This is a classic example. Does it? It doesn't. It touches my pencil twice. Therefore, the answer is no. This is a really useful write down the answers and review it and put it in your notebook. Okay, guys? I'll see you soon. Bye-bye.